Yeah, what am I here to talk about? So the title says I'm going to be talking about something called Featran and some function f and finding values for the weight vector that gives us some vague notion about the best future results. Let's not worry too much about what this all means because that's kind of the other big part of machine learning. And we'd be here all day if we had to really dive deep into that. So let's just leave it as, if we go back to our housing price example, we think that some function f is a good model for giving prices based on the features in X. So let's take some housing data where we already know the price, and then we're going to apply some iterative algorithm to update this weight vector until we converge to an optimal solution. And then once we find the values of this weight vector, we can make predictions on prices using the same properties for future data, where we don't know the price by just applying this function. So sorry, I kind of breezed through that, but hopefully it makes enough sense to sort of contextualize everything. Yeah. So all of that said, if we split up the general process of machine learning into two distinct sort of categories, over on one side we have all the really sexy kind of academic world of, modeling, training, deep learning, all that sort of stuff. But just as important to successful machine learning systems is, I think, the other side before all of that happens, which is, selecting and transforming the relevant properties of our input data. And so, in other words, the process of generating this vector x that I mentioned. And I've been calling the components of X properties, but now maybe we can switch to the more widely used term, which is called features. So maybe we can call this subdiscipline of machine learning feature engineering. Yeah, and so one other thing to note is that some of the examples of features I just mentioned, like in the housing price example, so like neighborhood or city name, these are actually string values, but machine learning algorithms don't really know how to work with strings directly. So everything has to basically be encoded as some type of numeric value. So maybe floats or vectors of doubles, so we can pass them as input to a model. So kind of another important part of feature engineering is translating some of these features into a numeric representation. And so that being said, let's kind of take a look at some common types of transformations that come up in practice. OK. So here I'm defining a case class representation for a track in Spotify's catalog. And as you can see, it's got a few fields defined. So we have an ID, a name, an artist, and let's imagine we have some kind of audio analysis that we do on our tracks to determine which genre the song best fits into. In reality, a song can have multiple genres, and even then it's sort of like a loosely defined hierarchical sort of concept. But just to keep it simple, let's imagine we have, say, 40 or 50 top-level genres, and we just want to say which one fits the most. And let's have it be an option, because maybe it's been recently added to our catalog and we haven't run our analysis on it yet. Or maybe the analysis couldn't attribute a genre for whatever reason, so we'll have it be an option. And then let's also say we have a play count, which is just the total number of streams. And then, yeah, so below that we create a collection of a few different songs. And now what we want to do is apply some feature transformations to this data set. So I'm going to run through three common types of transforms here, and let's start with something called a binarizer. So what a binarizer does is basically turn an input into a binary value by applying some threshold. Okay, it's pretty straightforward. So maybe we want to apply this to our number of streams column, and here's how we do that. So we just map over the collection to have things be 1 if there's over 75 plays and 0 otherwise. And so maybe the reason for wanting to do this is to sort of partition our song catalog into two distinct categories. So one would be the very long tail of songs with relatively little streams, and the other being kind of the more popular tracks. And maybe we want our model to treat these two categories of data differently, but then sort of ignore differences within those categories. So maybe we want our model to treat a song with 1,000 plays different than a song with 5 plays, but then the difference between 1,000 and 10,000 could be ignored. Yeah, so as we would expect, we get back this list. So we get 0, 0, 1, 0. Yeah, and this was super easy. And at this point, you might be wondering, what do we even need a library for? Like, it just kind of seems like we're doing standard data processing, and it's not really anything special. So let's take a look at a few more examples. OK. So here's another type of transformation. So in this case, we provide a minimum and maximum value as a parameter. And then the input values are scaled to fit within that range. So the largest value in the collection will then become kind of the given maximum. The smallest will become the minimum, and everything else will be scaled accordingly. So this one's a bit less straightforward because we need to make a pass through the collection first to find the minimum and maximum values. So we'll do this one again with the play count field. And basically first we do a map to extract the plays field and convert to a float. Then we reduce to get the minimum and maximum play counts in the collection. And by the way, I think there's maybe another function we could probably use here. I'm sure some of you are probably wondering that as well. But I just want to leave it like this for now because I think it'll make it a bit clearer when we talk about some of the abstractions that will come up shortly. Anyway, so after we get our min and max values, which we see are 20 and 1,000. And then, yeah, finally, so we pass through the collection once again, this time scaling the play count to fit within the range we define. So, if we say we want our minimum to be 1 and our maximum to be 10, then, so we take a ratio of the difference between the play count and the minimum play count over the range within the data set, multiply that by the given range, and then add the minimum. So our output is this new list, and we can see our values are between 1 and 10, so that seems to have worked. OK, so let's look at one more common type of transformation, which is called one-hot encoding. So one-hot encoding means that given a categorical piece of data where there's n distinct categories, we'd want to turn each category basically into its own column. OK, so we get a vector of length n, and then we put a 1 in the corresponding position if a track is of a certain genre, and then 0 elsewhere. And this is used, again, typically for categorical features. So going back to the neighborhood example, or for this example, if we stick to that, music genres would be a good candidate. So looking at our collection of songs again, if you look at the genre for each song, you'll notice that there's 4 in total. We got rock, metal, hip hop, and rock. So first, we can basically build a set containing those genres. And then we basically map each one to its own one-hot vector. So that's what you see here, the 1, 0, 0, 0, 0, 1, 0, 0, and so on. And by the way, you might be wondering why this is the preferred encoding. We could have done something simpler, like just map each category to its own integer. And that can work too, but it also introduces like an ordering and a notion of distance between categories. So for example, metal could be given the integer 5. Classical could be given the integer 6. And depending on the problem, that might cause the model to incorrectly treat classical and metal as similar in some sense, because they're sort of next to each other on the integer scale, which will probably give some bad results. So one-hot encoding basically makes sure that all categories are at the same distance from each other because they're basically unit vectors on their own orthogonal axes, right? So that's why it's so common. So let's look at how we might do this encoding in Scala. First, we take our song list and we map out to extract the genre field. And then we map again to put it into a set to make sure we're not keeping around duplicates. Then we combine the sets all together with that reduce, so it's just set union. And then we turn it into a list to maintain a deterministic ordering. And yeah, again, this could have been written a bit more concisely, but I wanted to show each step clearly here. So great. And so with our list of all the unique genres from the song collection, we're able to produce the one-hot encodings by just mapping over the genres and sort of comparing to each song genre. And yeah, so we get the expected vector encodings. So now we've kind of taken a look at how to implement some of these transforms using just vanilla, Scala collection operations. We can now sort of start to imagine how this could get a bit cumbersome, and it might be worth designing a library around. And in a few slides, we'll talk a bit more about some of the concerns that might inform some design decisions. But let's start with some observations about the structure of the computation we've seen in these examples. So yeah, some of you might have noticed already that there's sort of a common set of steps we're taking with each of these transformations. And it turns out there's a fitting abstraction that's kind of suitable for all the major transformations we want to do in machine learning. So let's look at what these steps were. In each of the transformations, the first step was just to extract the right field from our case class. So taking the play count in the case of the binarizer, or genre for the one-hot encoding. And then generally speaking, there was this aggregation step in order to produce some sort of summary data. Okay, so like the set of distinct genres, or the min and max play counts from the collection. So it starts with another map to take our input type into an intermediate type. Then we reduce these intermediate types to a summary value, and then finally present them by converting to an output type. So this is basically the definition of an aggregator, and we'll see shortly how that comes up in the Featran API. But yeah, then finally after the aggregation, the last step is sort of just to map over the collection again to actually apply the transformation using the summary values. Yeah, and I'll just point out now that this is kind of the most general way we can represent the computation. But for some transforms, like the binarizer, which we saw first, we actually don't need the aggregation step at all, since it just needs like a fixed threshold to map over. That's it. And so in that case, it would basically be treated as like a no-op, unit aggregator. Okay, so after all the build-up, I think we're finally ready to get into the meat of what this talk is about, which is an open source library called Featran. And one aspect of this is, just about reuse. Like again, many types of feature transformations, including all the ones we just looked at, are used basically all the time in machine learning. And it would just suck to have all this boilerplate code kind of out there in the wild. Another concern is composability. So in typical ML problems, there could potentially be many transformations we want to do with our input data. And you can kind of imagine how unmaintainable it would start to get if we had to stuff all that logic into like a bunch of maps and reduces. So this kind of suggests we want an API that sort of can elegantly handle composing many of these together. And another concern in the context of production machine learning systems is being able to share as much as possible between when we train our model versus serve it later on in production. So yeah, we kind of want to make sure that features are transformed the exact same way for both training and serving. So a good design would allow us to specify what our feature transformation should be, but then kind of defer the execution and apply the same specification on both the training and the serving side. So yeah, this brings us to one of the key abstractions in Featran, which is something called a FeatureSpec. So this is the main entry point into the Featran API, and it's sort of like a DSL for specifying, given some type T, how to choose some property of that data and apply an associated transformation. So the representation here is really basic. It's just a class with two methods, required and optional, where basically you first provide an extraction function f, to take some type T to another type A. And then you'd supply something called a transformer, which we'll see in a minute, but it's basically a wrapper around an algebroid aggregator. And as you might expect, so required is something we would use for transforming features which we want to always be present, whereas optional allows us to specify a default value in case of missing features. Okay, so this is kind of a stripped down definition of the transformer class. There's a few other things in there, but again, it's basically a wrapper around an aggregator. And yeah, I've mentioned aggregator a few times now, so let's kind of talk for a second about what that actually is. So here's the trait definition. And again, this is something that comes from a library called Algebroid. Are people familiar with that? Algebroid, sort of? Yeah. So an aggregator has three methods. Prepare is basically just a way to convert the input type A to an intermediate type B. Semigroup is another type class, really, also from Algebroid that defines how to combine two things of a given type. Okay, so this is really the meat of the aggregation. So if we have a list of things of type A, we first convert them to type B, and then using the semigroup, we can combine all those B's into an aggregated B. And then finally, the present method is how we just convert to our output type C. Okay, so sorry for all the letters, but that's kind of how aggregators work. Yeah, and I just want to show a few helper methods that we use in Featran as well, because these just kind of make it easier to create aggregators for types where semigroups are implicitly available. Okay, so we can provide a function from type A to B, which is really giving an implementation of the prepare method. And likewise, we can do the same going from B to C to define a present method. And as long as there's an implicit semigroup available for B, this would just create an aggregator automatically for us. So anyway, this just kind of helps to get rid of some of the boilerplate. But now let's go back to our min-max scalar. And really, this is pretty much equivalent to what we just saw, except this time we're implementing it in terms of an aggregator rather than just vanilla Scala code. So the input type for this is obviously double. And then our intermediate type is a tuple, where the first element is a min of double, and the second is a max of double, since we need to keep track of both. And yeah, by the way, these min and max types also come from Algebroid. And we just use them here for type safety. So min and max basically have their own semigroups, which kind of describes how to combine them in the way that you would expect. And so we get that for free by using these types. And then the output type, which I just alias to C for space reasons, is a 2-element tuple of the doubles, containing the min value and the max value from the collection. And yeah, so notice that the output type is not the actual type of the output value, when we do the feature extraction. It's just the output of our aggregation step, which contains information that we'll use afterwards to actually apply the transformation. Okay, so going back to this feature spec thing, here's how to actually use it. And we'll stick to our song example and use the exact same transformations we've already looked at. So earlier, we defined the song case class with a few fields. And then, we went on to write a bunch of code to binarize the play count, scale the play count, and one-hot encode the genres. And that was a lot of work. So with Featran, what we do instead is we just define a feature spec of song. And then we build up the specification by basically chaining together a bunch of calls to required and optional transformations. And Featran has a bunch of standard transformations built into the library itself. But it's also really easy to extend by just implementing your own. So yeah, you can kind of see like Featran already defines these transformers that we looked at. And the logic of how those are actually implemented is decoupled from the site of the feature specification, which makes it easier to read, it's nicer to work with, and all that sort of stuff. But yeah, notice like so far there's no mention of the actual songs collection we created anywhere yet, and that's because we're not actually transforming the features yet. We're just kind of specifying what the features are, but deferring the computation until later. So then how do we actually use the specification? So what we can do is we can call this extract method on our songs collection, which gives us something back called a feature extractor. So let's look at this to see what's going on. Yeah, so we can see that rather than accepting just a sequence of some type t, extract actually takes a context-bound type parameter representing a collection type, which is something I'll talk about shortly, but then an input of input collection of that type. And the idea is we didn't want this API to be limited to just working on in-memory Scala collections. We wanted it to support collections from different data processing frameworks. So at Spotify, and of course we're not alone in having these kinds of requirements, but given our large user base and catalog and things like that, there's obviously tons of data that we have on hand. And in many cases, we need to be able to apply our feature transformations over a large set of records that's distributed over many machines. And so there's several processing frameworks out there that define abstractions to represent collections that can be distributed in some way. So think Spark or Flink. And actually at Spotify, we have our own open source Scala framework that Idris talked about yesterday called Shio, which we use for the bulk of our ETL jobs. But anyway, all these frameworks kind of define their own version of a distributed collection. And that's one of the things we designed Featran to support right out of the gate, just being able to work easily with different frameworks. So let's take a closer look at what this collection type is. Okay, so yeah, here's the trait as it's defined in Featran. We can see it's pretty simple. It just has a couple methods, which are map and reduce. And actually, there's a couple others in there too, but there's sort of minor implementation details that we can ignore here. So this trait definition sort of comes back from the observation we made earlier, right? Which is that the types of transformations that are usually done in machine learning can all be expressed as aggregators. And since aggregation can be implemented from just map and reduce, it sort of follows that as long as some collection type, whatever it is, we don't really care. As long as we can provide an implementation for these two methods, then we're able to apply the transformations to that collection. So basically, all the Featran transformers will work as long as we have a collection type available. So yeah, out of the box, Featran provides implementations for Scala collections, Shio's S collection, Scalding, Spark, RDD, Flink, whatever. And again, it's extensible to other frameworks too, as long as you can provide a collection type implementation. And just to show you, this is kind of what it looks like to use from a Shio pipeline. And again, something Idris mentioned yesterday is that Shio is kind of heavily influenced by Spark. So if you're familiar with Spark, this might look a little familiar. So yeah, we get a Shio collection of songs, and then we just call, FeatureSpec.extract on it, which will apply the feature spec over the distributed collection. So now this is actually happening as part of like an Apache Beam job. That's what Shio is built on top of. So again, all you have to do is end up with a collection of stuff you want to featureize, and then it's identical to the call we made earlier. on our Scala collection. And it works because there's an implicit collection type defined. OK, cool. So we've kind of seen now that Featran supports a handful of different frameworks, which is nice. But let's sort of get back to talking about the core functionality and look at some things we can do once we get our feature extractor. OK, so one handy thing is being able to grab the list of feature names that were given to each transformer on the feature spec. So going back to our feature spec we defined earlier, we get our extractor and then we can grab the names. It's not really a big deal, but it's useful to keep around, especially because, and I'm going to talk about output formats in a sec, but in some frameworks, the features actually need names. So like in TensorFlow, you end up building this map of features keyed on names and stuff those into a protobuf payload. OK, so maybe something a little more interesting and useful is, finally, we're sort of coming to parity with our vanilla Scala implementation, which is to actually get the feature values. And so all we say is extractor.featureValues and give a type parameter, which basically indicates what type we want our output values to be. So here we say we want them as a list of doubles, and that's exactly what we get back. And so this type parameter we pass in order to get the values brings up sort of another design concern of Featran in terms of just its flexibility as like a general purpose feature engineering framework. So let's take a closer look at that. So here's the definition, and you can kind of see it takes some type parameter f, again with another context bound called feature builder. So there's some more implicit magic at play here. And then we get back an m of f, and so you can remember that m is the collection type trait we already looked at. So let's go ahead and dig into this feature builder thing. Right, so feature builder takes a type parameter t, which is the type we want our feature values to be. So in our example above, that was a list of doubles. And let's just go down the list of methods here. So init is kind of self-explanatory. Basically, it initializes the output value, if it needs to be initialized at all. And this would basically be called once per input record, not per feature. Add is, adding a feature to the output record. And the name is used depending on the output value we want. So again, TensorFlow, we need that. But if we just ask for a list of doubles, it would be ignored. Skip is if we want to skip a particular feature value in the overall output record. So the total number of feature values added versus skipped should sum to the dimension. OK, and then, we can get the result and also provide a mapping to other types. Anyway, it might not be super clear why the trait's defined this way, because some of these methods are sort of like, low-level implementation details, just in order to work with certain types. But the important thing is really just being able to add feature values to our output type. Okay. So here's a few of the available types that Featran supports. So we have Scala traversable, sparse and dense vectors from Breeze, again, TensorFlow's example protobuf, and et cetera. And again, it's extensible if you want to provide your own output type. It's just a matter of writing a feature builder. And just to show that this works for one of these other types, let's go back to our feature extractor. And this time, we're asking for feature values as sparse vectors. So we just say feature values of sparse vector, and that's the output we get. OK, so let's look at another thing we can do with our feature extractor, which is get something called the feature settings. And this is basically an object that holds all the summary values computed during the aggregation step, and also the parameters needed for the feature transformation. So it would have things like the binarizer threshold, the range parameters for the min and max scalar, the actual min and max from the collection, our genre vocabulary, all that sort of stuff. And so going back to our discussion about machine learning from the beginning of the talk, we'll remember that there's kind of two places in a production system where we want to apply feature transformation. So initially, we need to transform our training data set, which is basically, it's data that's used as input to our model training framework. And then, once we have that model, we're able to take it and apply it to new data, right? And that data needs to be in the same format as our training data, which means we basically want to apply the same feature transformations on the prediction side. The difference is that on the prediction side, we don't want to redo the aggregation step all over again with new data. We just want to use the parameters and the summary values from our training step. So this is why Featran exposes this information. And actually, it also has an API for reusing these settings to perform extraction on additional data. So let's see what that looks like. So yeah, it's pretty straightforward. You just call extract with settings, and obviously it needs the extra settings parameter. And so yeah, like I said, this is pretty useful when it comes to serving our model in production, because this will actually work in both like a batch prediction or like an online, backend service setting. And that's exactly, what we do in many of our backend services internally at Spotify. Cool. And so yeah, while we're talking about the similarities and differences, between the two worlds of model training and model serving, another really useful thing Featran provides is the ability to combine feature specs. So here, we're doing the exact same feature transformations as before, but instead of putting them together in a single feature spec, we have it split up so that the binarizer and the min-max scaler go together in the first feature spec, but the genre encoder goes by itself in the second one. And then we stick them together by just creating this multi-feature spec object, and then we can get the exact same results as before. Now, why would we want to do this? So again, going back to the setup of our machine learning problem, there's a class of problems, again, called supervised learning, which basically means that we train a model to predict something by using training data that's already labeled, with the right thing. So in this case, let's say we're trying to do genre classification, where we have some track data and a bunch of features about that track that our model will learn to use to predict which genre it belongs to. And so at training time, we need data that's already been labeled with the right genre. And so there we would use the full combined feature spec. But then at prediction time, since our inputs obviously won't have a genre, we just need to use the component feature spec that has the label basically removed from it. So just maybe to make this a little bit clearer, let's rename the feature specs. And yeah, this is like a super common pattern for teams that use this in their machine learning pipelines at Spotify. Yeah, so again, we have the same two feature specs. This time they're called features. The first one is features, the second one is label. Again, at training time, we combine them to do the feature extraction, and at prediction time, we just use the features part of that. Now, yeah, just kind of an aside, like a genre classification model would probably be pretty garbage if it only used these features related to play count. I'm sure there's other things we can think of that would give our model a bit more information, things like beats per minute, length of the track and stuff like that. So this is not a realistic example. Yeah, but anyway, so while we're talking about prediction, it's common to want to serve this model in an online setting. And what I mean by that is being able to use a trained model in a backend service to make predictions with live traffic. And at Spotify, all of our backend services are in Java. Kind of a shame. But this paradigm still works pretty well. And so what people end up doing is they package these feature specs into a jar and publish it. And then the backend service can just depend on it. It's JVM. And so they pull them into their backend services, load up the model, and then they can featureize data and serve predictions. Okay, so since I still have some time left, I want to talk about something else quickly we built at Spotify called Noether, which is another part of our open source Scala machine learning stack. It's named after M.A. Noether, who made a lot of contributions to abstract algebra and theoretical physics. And anyway, it kind of turns out that there's another area within machine learning where aggregators are also a useful abstraction, and it's called offline evaluation. And so offline evaluation is basically a process where after we train our model, we want to check how it performs on a set of held out labeled data by basically comparing the predictions versus actual labels and then computing some metrics based on those comparisons. And this is really critical in production systems because it basically functions as sort of like a QA step before deploying a new model to production. So Noether helps out with this by providing a bunch of aggregators that can compute these common metrics. So let's look at a quick example. Right, so one useful thing machine learning engineers want to look at during model evaluation is something called a confusion matrix. And it sounds really scary, I promise it's not. It's just a table that basically has all the counts of like the false positives, true positives, false negatives, and true negatives in a binary classification problem. I'm not going to go through the details here, but spoiler alert, it's an aggregator. So yeah, using it looks something like this. We build a collection of these prediction objects where the left element is the actual class and the right element is the predicted probability. Yeah, and the probability gets turned into an actual Boolean prediction by applying a threshold with the default set to 0.5. That's pretty standard for binary classification. And then we just aggregate using our binary confusion matrix aggregator provided by Noether, and this is the result we get. So yeah, the first element is a true negative because 0.1 is less than the 0.5 threshold. The second is a false negative, and the last is a true positive. So there's no false positives, and so we expect this matrix that we get back. Anyway, so that's Noether. It's a small library, but it's pretty useful for computing these kinds of metrics. Yeah, so that's basically all I have to say. Just to kind of quickly summarize what we talked about. What Featran gives us is an expressive, kind of concise API for featureizing data without coupling it to a particular processing framework or a particular output format. And it was designed for reproducibility by way of this shareable feature spec that sort of guarantees equivalence between training and serving contexts. So that's it. Thanks for listening. Here's a link to the repo on GitHub if you want to check it out further. Again, it's open source, and we love working with the community on a lot of our projects. And then I threw a couple links to some of the other projects I mentioned, so you can check them out as well. Thank you. Questions? Yeah. Great question. So I'm not a machine learning engineer, full disclosure, so I couldn't tell you. I think we have some people doing some convolutional stuff with TensorFlow. TensorFlow is really big at Spotify, so yeah, we're pretty heavy users of that. But yeah, I can't say any more, unfortunately. Yep.
Although you just ended with you can't say anymore, but I was going to ask, your use of TensorFlow, is it all through like the Java interface, or
great question. So we use Java only for serving TensorFlow models, so we don't use it at all for model training. I'm not even sure if like is there like a Java training API? Maybe it's like really lightweight, but yeah. So that's a great question because we do our featureization in JVM, but then a lot of people use TensorFlow, and so we actually at Spotify we sort of standardize. So I said here that we can write things as TensorFlow example protobufs. Which that's a programming language agnostic format. It's just protobuf. So, and it's really nice that it works well with TensorFlow. So people still use the Python API. Yep.
On that, you're growing your list of Spotify open source ML contributions. Do you think there's going to be, or are you guys pretty happy with training in Python?
Yeah, I think we're pretty happy with Python. Yeah, we don't really have like a blessed kind of training framework that we use. I think a lot of people just really like using TensorFlow and some of the higher level APIs on top of that. I think there's maybe one team that uses MLlib in Spark, but yeah, I don't think we're gonna invest more in like the JVM stack anytime soon for model training. So, yeah.
Are there any other repos like Featran, or you guys have just made Featran for your application?
Great question. So, the question was, are there any other repos like Featran? And feature engineering is not like a Spotify-specific problem. It's a domain problem. It's a machine learning thing, and a lot of machine learning frameworks have their own featureization library. So TensorFlow has its own featureization library. Spark. I'm not super familiar with MLlib. I would imagine it has its own featureization library. Scikit-learn has its own featureization library. For us, the value proposition was that we wanted people to be able to write featureization once and be able to swap out their model training framework if they want and still have the featureization code untouched. The other big part of that is that we're heavy users of this thing called Shio. And so that's a Scala library, and it adds a lot of value for teams if they can stick with that for doing the featureization. So. I love Beam. So yeah, Beam, it's Apache Beam. It's kind of it's a unified batch and streaming API, I think based on Flume Java or whatever that paper that Google wrote. But it's great. Yeah, we're really heavy users of Beam, so yeah, it's awesome. Highly recommend it. Yep.
Just a follow-up question: are you using Beam on how are you using it in Google Cloud?
We are, yeah. So Beam, Beam is kind of like it's almost like a sort of front end, like model for computation. But so I think there's backend. So there's a Flink backend for Beam. There's a Spark backend. But yeah, we use Google Cloud Dataflow. Yeah. So all of our stuff is on GCP. Cool. Okay. Thank you very much.